thank you, Dr. Hunter, for letting us come into your office this morning and ask you these questions. Addison is wondering how many operating telescopes are there globally, and can they all be connected via interferometry? So if you wanted, could you connect the VLA to the other interferometry sets that are out there? Like, can we combine everything on the planet, or is it the VLA works only with the VLA and the other ones are separate?
Edison, we can't collect all the telescopes on the planet, and the reason is connecting them all together is complicated and hard. But it's been partially done in the sense that I referred to this telescope that is an interferometer that is much larger than the VLA. It's called the very large.
Is it the VLBI?
The very large baseline interferometer. Thank you.
Yeah. Okay.
And so this has, when the VLBA or VLBI is operating, it uses, and I don't remember, it's half a dozen or so different radio telescopes across the globe. One of them is part of the VLA, so they'll take it out of the VLA to use in this VLBI. And then the others are scattered around the globe, and I don't remember where all the locations are. But it lets you use, the diameter of the Earth as your limiting size. But people work really hard to put those half a dozen telescopes together into working together as an interferometer. Mm-hmm. And so, no, we don't. There are other interferometers. There's in Europe, for example, that work at the same wavelengths that the VLA works at, but they, as far as I know, they don't work together as in concert.
Okay. There you go, Addison. Something for you to work on.
Yeah, that's right.
Okay, couple more. Ben is wondering, is it possible to build a telescope that collects microwaves, and what would that tell us about the universe?
So Ben, I'm going to answer your question a little bit differently than what you asked. You asked about microwaves, but there is a fabulous new interferometer that works at millimeter wavelengths. Which I want to tell you about. Okay. So I'm using your question as an opportunity to answer this question. It's called ALMA, and it has been built in the Atacama Desert in Chile.
Okay.
So when I use the VLA, I use it to observe atomic hydrogen gas in galaxies.
Okay.
But with the ALMA, we can observe molecules in galaxies. What's really interesting about cold molecules is that cold molecular clouds is where baby stars are formed. Awesome. That's where the new stars are formed in the galaxy, and in other galaxies. So if you go out at night and you look at the middle of the sword in the Orion constellation, that middle of the sword is a little nebula. It's called the Orion Nebula.
Okay.
And that is that's the closest place to Earth where new stars are forming in the Milky Way galaxy. So molecular clouds are the key place, the key step. Forming this molecular cloud is a key step in forming new stars in galaxies like our own. And we see these beautiful structure of molecular clouds.
Wow.
So I'm going to tell you a little bit about what I do, because I just used ALMA a few years ago, and I found somebody else asked a question about what's the most amazing thing that you've seen.
Dagan asked, what's the most amazing thing you've seen?
So Dagan, this is the answer to your question about what did I see that amazed me, and this was observed with ALMA, between ALMA and another telescope called Herschel.
Okay.
Which is a space telescope sent up by the Europeans, but we got telescope time on it. So a little bit of background. I study tiny little dwarf irregular galaxies, and I have a picture of one over there if you want to take a picture of that. But it's an example of the tiny little galaxies that I study. They're the tiniest galaxies in the universe, but they are the most common. And what's cool about them, one of the things that's really cool about them, is that they don't have very much in the way of heavy atoms. So galaxies started out as hydrogen and helium atoms. And then all of those heavier atoms like oxygen and nitrogen and carbon and all the things that are important to us here on Earth, those atoms were made inside of massive stars through nuclear fusion. And then as the stars die and they explode and they spew these heavy elements out into space, they pollute the galaxies. And that pollution is what we're made of. Right. But okay, and so over time the galaxies get more and more polluted with these heavier atoms. The little tiny dwarf irregular galaxies have much less of these heavier atoms than a galaxy like the Milky Way. And also less dust. Dust is made out of silicon and carbon, and the Milky Way has a lot more dust than these little tiny galaxies do. But it turns out those heavy atoms and the dust are very important in helping to make those molecular clouds and helping them to protect the hydrogen molecule. The hydrogen molecule is very fragile, and the molecular cloud is bathed in the ultraviolet radiation from stars, which would break apart the molecule. So these oxygen, and especially carbon and the dust, form a skin around the outside of the molecular cloud. Just like your skin, if you go out and you get sunburned, your skin gets sunburned, but your organs inside don't get sunburned because your skin has stopped that ultraviolet radiation. So in the little tiny dwarf galaxies, which don't have as much skin, or they don't have as much oxygen and dust, or carbon and dust, the ultraviolet radiation penetrates in further. So you end up with a thicker skin and a tinier core in the center. And so what are the consequences of that? Well, I don't know. But we set out, so people had said, well, this happens. We set out to observe it. So we used the Herschel telescope in the far infrared to observe the carbon. So we took a picture of a region in a little dwarf galaxy which was forming stars, and we saw, and we took a picture of the carbon which is in the skin. So we have a picture now of the skin in this star-forming region, and it was really thick, okay, and it had a bowl in the center. It was like this bowl. There was a, there was a ridge around here and a depression in the center. And then we used ALMA to map the carbon monoxide in that region, and inside the bowl we found half a dozen tiny little raisins. Or the raisins here are these molecular cores. So we looked in this bowl and we found these tiny little cores, just like it had been predicted, a thick skin and tiny little cores of molecules. And that was the first time we were ever able to take a picture of the structure of this molecular cloud at this low of abundance of heavy atoms. And to me, that was incredible.
Yeah, that is incredible.
We just looked at that and, wow, wow, we're actually seeing the molecular cores at this low metallicity where nobody had ever seen it before.
Yeah.
It was really amazing. Now, of course, here's the real question. What difference does it make?